Okay, good afternoon, everybody. I hope everyone's having a wonderful day. So before I get started, I just want to remind you that Assignment 1 is due by the end of Wednesday next week. Keep in mind, like I said the other day, I'll accept your submissions up until 8:30 in the morning. So you will have that time if there's any technical issues, or if you want to make use of that time, you're welcome to it. So keep in mind, this is till the end of February 2nd until the 3rd at 8:30 in the morning. Okay? Just to be clear. You'll see that on the course website. I include that note. So, that being said, that's coming up. So, anyways, I want to pick up from where I was last day. Are we okay with proceeding? Are there any questions before I proceed? Are we all good? If we're all good with this, give me 2 thumbs up. Oh, wonderful. Wonderful. Okay, so I'm going to proceed, and let's talk more about asymptotic notation. So this should be the last lecture really focusing in on this topic. So before I get started, some of this, like I said, you may have seen previously. Other parts of it, maybe we're going to go a little deeper than maybe you've seen in 210. Perhaps not. So first, before I proceed, I want to just make sure that everybody's aware of some commonly known classes of functions. So very often when we study different kinds of problems, and we want to know and classify those problems by the complexity required to solve them, so when we measure their complexities for solving them, we often will be trying to lump those problems into based on their most efficient algorithm. Likewise, when I have 2 different algorithms, I would like some way of talking about, say, one algorithm versus another, which we've talked a little bit about in previous lectures. But I just want to make sure we kind of have a name to associate with different well-known classes of functions. So many of these you're familiar with. So for example, big O of 1, we say that's constant time, if we're talking about time complexity. Log n, keep in mind, notice I didn't write the base. The base doesn't really matter. One thing I want you to convince yourself of, you may be get the idea of this while working on assignment 1, is that the base of the logarithm really isn't that important, as long as it's just some constant. Because there exists, for example, the change of base formula for logarithms that you could always switch from one base to another. And when you do this, you actually just introduce another constant factor that varies between one logarithmic function to another. So you'll find very often I won't even mention what the base is when I write it like this. But if I want to be more explicit, I will often write the base. But you'll find when you talk to a lot of computer science folk, normally what they'll say is, when they say log n, they usually mean log base 2 of n anyways. But I feel like I need to mention that. And then there's many of these you're familiar with, like linear. You may know of big O of n log n, that's log linear. We've got quadratic here, so that's n squared. Just as a quick question, can anybody tell me what's n again in this expression over here when we're talking about complexity? What is that? So what am I measuring all my complexities by? Exactly, the input size. Perfect. So that's what n is here. Perfect. So let's see, we talked about quadratic. Polynomial, this will be an important classification for us a little later on. So this is all the set of functions that include those that are in big O of n to the c, where c is some constant that is non-negative. So for example, that will include like big O of, like say if you have all your quadratic functions, your linear functions, your cubic functions, all of these are polynomials. But notice the use of big O notation here. So remember, this is an asymptotic upper bound on the complexity. So for example, if somebody gives you a function that looks like n log n, and somebody asks you, does that run in polynomial time? The answer is yes. The answer is yes, because it's not going to run any longer than any one polynomial function. So is that clear, everybody? So that's why I'm using big O notation here. In contrast, there's this gap that persists between 2 major classes of complexity functions that you're going to run into when we start studying some problems towards the end of this course. And sometimes it's going to creep its head out every once in a blue moon. and I'll try to like point it out to you, is that there's also this class of complexity functions called the exponential functions. I'm sure you've seen these before, but these are your ones like 2 to the power of n, 3 to the power of n, and so on. Then if you really want to get out there with things that are going to have really, really high growth rates, we're talking about not even just exponential, but factorial. These are ones, if you had an algorithm that runs in time that's factorial in n, that it's going to take a long time for even, I would argue, not even that big of n. So just be wary of that. So for some problems, you'll often be working with problems where maybe stuff like this might pop up for a quick answer. And then you have to think a lot more carefully about if maybe you could get a polynomial time algorithm. But for other problems, such as many of the ones we've talked so far about, we often are working kind of in this domain, about usually around over here. And usually we'll talk about those polynomial time, running time algorithms, usually as efficient algorithms, in contrast of the exponential and below as sort of inefficient. But it typically depends on the problem. We'll talk more about that towards the end of this course, kind of talking about, okay, so there exist problems we don't know if there exist efficient algorithms or not. And often the best knowledge we have about our best known algorithms usually kind of sit over here where you're going to have exponential time required based on the best known knowledge we have at the time, but we don't know if we could do any better. But there's going to exist a whole bunch of problems that exist where the best known algorithms all sit in these categories. And then lastly down here I have big O of n to the n. I didn't even know what to call that. This is just, no, just don't do that. So unless there's usually only a very small pool of problems that you're going to run into in your daily life or practice that you're going to really require this. I just call that oops. Just be careful with that one, okay? So are there any questions about these? I expected you have some understanding of some of these terms already. I'm just trying to remind you or refresh you on some of these. Okay, so if we're okay with that, first, are we okay with that? Give me 2 thumbs up if we're good with this. Because I want to start talking about properties that asymptotic notations have. Excellent. So let's head on over this way. Walking on down. Da, da, do, 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 do. So we're going to start talking about different properties. I'm going to try to motivate why you might be interested in some of these properties as we explore. Whoops. Let me get the camera there. It started doing the weird thing there. Let me just fix that. There we go. My apologies. I seen that one coming. I see that one coming. I'm looking over there. I'm like, uh-oh. Here we go. Hopefully we're all looking good now. Okay. I looked at over there. I'm like, uh-oh. Let me run over there. Okay. So we're going to talk about different properties for asymptotic functions. Asymptotic notations. So imagine I have 3 complexity functions. I'm going to call them f, g, and h whenever I need them. I'm going to talk about some of them. And then other ones I'm going to show you the property, but also going to prove it for you. For most of these, I'm going to include the full proof in the notes for you. So that if you wanted to take a look and say, hey, look, okay, so how do you prove this? I will have for most of these the proof sitting right there in the notes for you, okay? So we'll do 1 or 2 examples here in class. So the first property I want to make you aware of, and I must stress that unless otherwise stated, you may as well assume that when I say this property, that it holds also for big omega and big theta. So if I were to put big omega here, this property should also hold in that case. If I put big theta there, it should also hold in that case. So I'm just usually writing this out with big O, but keep in mind it also will hold for those other asymptotic notations. There will be very specific cases where after this I'm going to show you a couple more that hold for specific asymptotic notations. So here's the first one. It's called reflexivity. You may have heard of the reflexive property. Here's the very easy way I like to explain this to people. Is, okay, you have the thing. The thing has the property. So what I'm saying is I have a thing, my complexity function. I can tell you that because it's reflexive, it is big O of the thing. So that's what the reflexive property is. Just as a question for you, could you think about, if you've seen this right here, what you could pick for C and N0? So just by staring at that, does anyone have any ideas? Yeah, I see it in the chat there. So remember that at the end of the day, you're going to try to find that C and N0 as such that, in this case, it would be F of N is less than or equal to C times F of N for all N greater or equal to N0, right? Well, if I just make this a 1 right here, then it's F of N is less than or equal to F of N, which has to hold for all N, right? Because it's the exact same complexity function. So does everybody see that? So for some of these properties, you're going to see that you're going to just invoke what it is telling you. So in this case, there's no real conditions other than it's a complexity function. But it always will fall back to, here's the definition of big O. I pull out that definition and I try to find C and N0 and I use the bits and pieces I know. That's how the game plan will play out when you ever want to prove any of these properties. For most of these, at least, that's a very natural way of approaching it. So, if you ever find yourself working with a complexity function, you could just simply put big O around it and it's true. It's just, it may not look the prettiest. So, don't give me a really ugly looking complexity function that's like, oh yeah, look, I have like, I don't know, like 1/2 times n to the 4 plus n cubed minus n plus 1,000. Now, at this stage, you'll know some tricks that you can use to simplify this down, right? I must stress that technically it's true that you could just do this to it, and that's actually true as well, right? That's what I'm saying with the first property, but normally this is not what you'd like to write down unless it's highly relevant for your analysis, which in our cases, that's almost never going to be the case. So are there any questions about the first property? Does that one seem rather straightforward? I think that's pretty nice. It's a pretty nice property. So the second one, this one you may be familiar with as well. And so constants independent of the input do not matter. So it's just a general rule for us. So you may know of the rule, for example, that if I have constants that are just sitting with my complexity function, or multiplicative constants that are just sitting in front of my terms that are related to the input, well, those you could usually just drop and then you take the highest order term, right? That's typically how you play around with big O notation. So this is just a codified version of this for the multiplicative constants that could exist in front of parts of your functions. So it's meant to be a very simple way of representing that kind of rule. So if I give you some positive real constant, k, and I tell you that f is big O of g, then I can tell you that k times f is also big O of g. I see the g is kind of cut off over here. I kind of squished it in, but it says k times f is big O of g right here. But yeah, this is just one formulation of that rule that you've seen before. So it's just one variant of that. So there's not a whole lot I have to really say about it. You have some familiarity with it. Here's the third one. Now, this is the one that if you took this rule and combined it with this rule, you'll get essentially the rule that you're familiar with. So the next one is take the largest function over functions in a sum. So if I tell you, if I give you f and g and I add them, this is big O of the max among these two functions. So for each n, if I just take the larger of the two values that get outputted from each f, or if say one is truly dominating over it for all n, I always just pick the one that's the larger of the two. In most cases, it will be such a case. So for example, if I had like n cubed plus n squared here, if I take the larger of those two, right? If I wrote down n cubed plus n squared, you would tell me that's big O of n cubed, right? This rule is an easy way of getting that. So I want to prove this one with you, just as an example. So let's proceed with that. Actually, before I proceed, I also want to bring up another situation where you could run into this. So very often, like in the example I gave you about usage of big O notation, do you remember when I told you that, oh, imagine you want to sum up all the operations from different parts of an algorithm. Like say I have this first part of the algorithm, then I have the second part of the algorithm, then the third part of the algorithm. And you'll very often have it where I say, okay, I take the one, whichever one has the most dominant term, if I have all a bunch of them expressed in terms of big O. It's really just this rule in disguise. So if you have several parts to your algorithm, say there's actually two phases, for example. Say you have a first part of your algorithm, and say that takes, you find it some function that, say, for example, like I said before, say if the first part of it is some cubic complexity function. I don't know what else of it looks like. The point is that, say it's cubic, and then I have a second part of the algorithm, and say that takes quadratic time. What this property would tell you is that you take the larger of the two functions over your sum. In this case, we know that n cubed is always going to be greater than or equal to n squared for all n greater or equal to 1. So that means that I could just simply, because I know that about these two functions, I would tell you that this is big O of n cubed. So that's really just this property in disguise, right? So are there any questions about the property itself? Is this crystal clear? Okay, so like I said, a lot of this I'm just formalizing things that you may have heard before. So let me just walk on over here. In fact, I'm just going to kind of take a little, I'll just take a little fun, I don't know what I would call it, a stroll? I don't know. Let's walk over here. And let's prove this. And I want you to keep in the back of your mind as we're doing this, the method for which I'm going to do it. So like I said earlier, if I use the definition of big, well, camera, keep going, keep going. There we go. Wanted to take a break on the middle there. So let's try proving this, okay, everybody? So remember the game plan that I mentioned earlier when we did the first property. At least this, we sketched out the idea of it. Is I invoke the definition of big O, but I use the information I have to help me do that. So in this example, I know I have an F and I have G. I'm going to try to use those two complexity functions in a way to derive me a constant C and a constant N0 such that I get the property. You're going to see that with our second example that we can do something a little bit more sophisticated once I know extra information. So here's an example of us doing this. So remember, I'm just going to do it the same way we did it last time. So we find constants. So I find C. Remember, C is a positive real number. And N0, which is a positive integer, such that for all n greater or equal to N0, f of n plus g of n is less than or equal to C times the max among f of n and g of n. So I'm going to give you a little bit of intuition behind what we're going to do here, okay, everybody? So remember what I said last day, how I want to make what I have and what I'm trying to establish look like whatever's inside the big O. I'm going to use an idea that's just like that here. So that idea that I kind of sprung at you, I'm going to try to kind of mesh it into the way I'd prove this, okay? So I want to show you kind of like the way you can easily extend this idea to more complicated things, like arbitrary complexity functions. So if I have an f and I have a g, now I don't know which one is the larger function for value n. That I don't know, right? I don't know that information. I don't know. I don't know what f and g are. All I know is they're complexity functions. So my rule has to work regardless of this. So I have an idea here. What if I could make it so whatever's sitting right here is completely oblivious to the fact that one of these might be bigger than the other one? So for example, if I know, say, f is the smaller of the two, or maybe they're even equal to each other for a value n, that I have enough of the bigger one to beat out the smaller one. So does everybody have any ideas of how maybe I should pick C then? So does anyone have any ideas of how I should maybe pick C based on what I said? Just think about it carefully. Yes, I see it in the chat. Let's try C is equal to 2. Because remember, I have an F and I have G there and I'm adding them. What if I can make it look like something like, okay, I take the larger of these two plus I take the larger of these two. Then I could do what I did last day with my bucketing trick, right? Remember with my buckets? The other day, I could do that exact same trick. The one I showed you the other day. Isn't that kind of neat? So I could just do the same thing. That's at least where we're going to go with this. So watch this. So pick C is equal to 2. Then, now I just got to tell you what I'm going to do next. Then we find n0 so that for all n greater or equal to n0, f of n plus g of n is less than or equal to 2 times the max. I'm sort of running out of space, so I'm going to kind of squiggle this in. The max of f of n and g of n. This is just what I wrote over there. I put the 2 in. Now watch, just watch. You're going to see the same idea that I used last time, just again. But I can talk about something a little bit more general now. Sorry, I'm just running out of air. I'm just really excited about this. Well, for all n greater or equal to 1, both f of n is less than or equal to the max of f of n and g of n. We know this because if, for example, g were bigger than f for a value n, this max function will pick it, right? And now that just means simply this is true. If f was the bigger one, the max function will select that, and it'll compare it against f of n, which in that case would be equal, right? So both f of n is less than or equal to the max of these two, and g of n is less than or equal to the max of f of n and g of n, right? By the exact same reasoning. So now, here we go. So now I have both of these pieces, and I'm going to use the exact same idea I used last day. So if you thought what I was doing last day with those bucketing and how I summed over all the inequalities, that would seem really easy. That's exactly what we're going to do now. Watch this. Watch this. So for every n greater or equal to 1, f of n plus g of n, because remember, if I want to talk about f of n and g of n, I can simply collect up all of the things on the left-hand side of both these inequalities, and I can collect up everything on the right side of these inequalities. And notice if I add up over those sides, I end up with that right there, where c is equal to 2, right? So f of n plus g of n is less than or equal to the max of f of n, g of n, plus the max of f of n, g of n. Which, of course, this is equal to 2 times the max of f of n, g of n. So what should I pick for n0 then, everybody? What's n0 here? It's 1. Yes, it is 1. It is 1. So choose n0 is equal to 1. Therefore, by the definition of big O, because remember, we have to invoke the definition of big O at some stage of this, because I found C and N0. Those are for my definition. Therefore, that says by the way, by the definition of big O, f plus g is big O of the max of f and g. And that's the end of the proof, believe it or not. So do you see how all I did was use the same ideas that I used last time? But now I'm not talking about specific complexity functions anymore. This works for any two complexity functions. But I use the same kind of strategies I used last day. Is that kind of cool? So are there any questions about this? Did Dan come up and pull this out of his pocket and just showed you some, I don't know, some candy wrapper or something? Or does this make sense to everybody? So if we're okay with this, either way, if you find yourself looking at this, I recommend you take a look at it again. If you have any questions afterwards, bug me about it. I'm very happy to talk about it. So why don't let's talk about some more properties, okay, everybody? Let's head on over that way. So notice that our proof over here directly used the definition of big O, but I didn't really have a whole lot of extra information I was working with other than, oh yeah, there's two complexity functions and there's this max function. The max function does all the heavy lifting in that proof. So what I mean I'm relying on the way the max function works. So here's another one. This is one that you may have seen before. Adding two functions of the same order. When I say order, I'm referring to the asymptotic notation. Same order like big O. Produces a sum of the same order. So just to elaborate on what I mean by this. So if f is big O of h and g is big O of h, then if I sum f and g together, then f plus g is big O of h. So you might ask, Dan, how exactly would I run into this? So suppose I gave you two complexity functions, and for both of them, you analyze them and you determine some big O for them. So you find out what both of these are, and you want to execute each one after the other. But you know that both of them, for example, take quadratic time. But I execute the first one, it takes quadratic time, then I operate the second one and it takes quadratic time. What this property is telling you is that the overall running time will stay quadratic. So that's the natural way you could look, that's one way you could interpret and use this property. So is that clear, everybody? Are there any questions about how this property looks? You'll notice it's a little bit different than the other ones because now I have more information I can use. Notice it's a conditional statement. It says that if f is big O of h and g is big O of h, then the sum of f and g is big O of h. So I have two pieces of information. If both of these are true, then it follows that this property holds. So, does everybody understand this property before I proceed? Because I want to prove this one with you. Because I want to show you an example of, okay, if I have this information with me, how exactly do I prove it? Because it isn't just like I invoke the definition of big O once. You're going to see that I'm going to need to invoke it probably a couple of times. In fact, there's probably several ways you could prove this property with some of the things I've shown you so far. But let's try proving this together. So I'm going to just pick up the exact same game plan I did before. Remember, I need to find those constants. That's the end game for me. Once I have those constants, we're done. I just have to tell you that it's by the definition of big O, it has to hold, right? So, to prove the claim, we find constants. We find constants. C, remember C is a positive real number. And n0, which is a positive integer. Such that f of n plus g of n is less than or equal to c times h of n for all n greater or equal to n0. So remember, I'm just tolling out the exact same things I've done before. There's no weird black magic I'm pulling out here. We've done this every single time, right? So, but I have more information. And what I'm going to do is I'm going to use that to my advantage. So when I prove this claim, I'm going to use the fact that I know this, and I know that. And each of those tells me a bit of information involving the definition of big O, right? Because remember, if f is big O of h, what does that mean? It means that there's constants that exist that demonstrate that, right? Likewise, for the second one, g is big O of h. There has to exist a pair of constants, c and n0, just like when we did it over there, right? Just like we did previously. So let's use that information to help us. Both f is big O of h and g is big O of h, implying there exists constants. Now, I'm going to just make this a little bit easier for myself. I'm going to write it all into one longer sentence. If you find yourself just like looking at this, or if you're working on your assignment and you're trying to prove one of these kind of properties, you can always spell it out in a couple of sentences instead of doing it all in one sentence. I'm just doing that just to show you that it's possible to do it in this very simple way. Implying there exist constants, C1, C2, so those are the names I'm going to give those positive real constants in these two cases. And N1, N2, which are positive integers, such that, now, remember, I now have two pairs of constants. One pair is C1 and N1, the other pair is C2, N2. What we're going to try to do is I'm going to try to use these constants to create C and create N0. So notice I'm going to use that information to help me figure out what C and N0 are. So this is going to be quite a bit different than what we did last time, where you've seen where I was just like, okay, C is always going to be 2 or something like that. You're going to see that here is going to be dependent on information about these two conditions here. So, is it okay if I move over to this board by any odd chance? Is that all good? Because I just want to finish up writing this line, but I don't want to crunch it all down here for you. You don't need that much microwave writing. So if we're okay with that, I'm going to move on over here. So let's move on over here. Whoops. So let's finish up this proof. So to finish up that sentence, I need to finish saying what exactly this means, right? So I have those two pairs, I have the two constants, I have two sets of constants. I have ones for the positive real numbers, and then I have ones for the positive integers. Such that f of n is less than or equal to c1 times h of n for all n greater or equal to n1. And g of n is less than or equal to c2 times h of n for all n greater or equal to n2. So remember, all I did was pulled out the definition of big O, and I just told you what those two conditions meant. Does everybody understand that? I want to make sure I don't lose anybody at this step. It's an important step. In fact, when you're working on, say, your assignment, I would recommend you try thinking about how you could do this. Because it'll be the final problem, you're doing something quite similar to this. So, I have this here. And now what I want to do is now notice I have two inequalities here. Remember, my original conclusion for my conditional statement was that I have this part here, I have f plus g, and I would like to have something in terms of h on the right-hand side, right? Well, I'm going to sum over both these inequalities, and let's see what happens, okay, everybody? By summing, that says summing, the I is sort of melting into the M, let's fix that. By summing over both of the above inequalities, by summing over both of the above inequalities, now this is where you're going to see me pull out some nifty stuff, so pay attention to this very carefully here. So just like when you're looking at this, just be like, just get those eyes right in there. Just like if I was watching, I don't know. I'm really excited here. I'm hoping you're going to see how this one little step is going to play out. So let's see here. When n is greater than or equal to the max of n1 and n2, so I'm going to take the larger of those two values, because remember, when I sum over both these inequalities, I would like the overall inequality to be true. So what I need to do is I need to pick out the larger of those two values, because remember, if I pick, say, a larger value of n0, that's okay, as long as it works. In this case, this will ensure that if I were to invoke both of these, and I sum over them, most certainly it has to hold when I add these two inequalities together, because now the n1 held for that inequality, and the n2 held for this inequality, for all n greater or equal to each respective constant. So I'm just making sure it's big enough. So now, when I put it all together, I get f of n plus g of n, which is going to be less than or equal to this part here, c1 times h of n, plus c2 times h of n. Remember, that's right here. And now, remember, I want to get something that looks like something times h of n. Does anybody see how I can do that here? How can I make that look like something times H? Yes, perfect, perfect. So notice that if you were to, because I wrote these parentheses to help you see what I'm doing with these two, but really, both of these terms involve H. So I can take them, I'm going to factor out H of n, and I'm going to be left with C1 plus C2 together. So I'm going to have C1 plus C2 times H of n. Now, I have a question for you. What should I pick for C and N0 now? Because remember, our goal is to find C and N0. Do you see what I could pick now? Any ideas? So let's see here. So now I must stress that we don't necessarily want to, because remember, you see, if you were to erase everything here in the middle, right here, and you just wrote down f of n plus g of n is less than or equal to C1 plus C2 times h of n. That looks awfully lot like the form we're looking for, right? So what should I pick for C? Now, it probably shouldn't be 2. Remember, that's very specific to a certain function, maybe. Maybe we need something that's a little bit more general. But I do like your guess. I think that's a rather useful one, because we had that last time, right? But yeah, no, look at this. See, watch this. Yes, that's what I'm looking for. So look at this. So imagine I make C this. And you can see f of n plus g of n is less than or equal to c times h of n. Boom, right? Just like that's the mic drop. And then I said that all of this works when I take the larger of n1 and n2. And as pointed out in the chat, maybe I should make n0 be the larger of these two, right? See, I think that works, right? So when we see, let's do that. So by selecting constants, C is equal to C1 plus C2. And N0 is going to be the max of N1 and N2. The inequality f of n plus g of n is less than or equal to c times h of n holds for all n greater or equal to n0, right? So I think we got everything here, right? We identified C and we found n0 and we made sure that they work, right? So let's put our conclusion in. Therefore, by the definition of big O, f plus g is big O of h. And that's the end of the proof. So notice that when we have a little bit more complicated statements, we want to use those conditional parts that we are given to give us information for how we can prove the claim. So all you got to think about is, what do those conditions mean? Just spell that out, and it often will give you some helpful information to figure out how to prove the claim overall. Sometimes it's true, sometimes it's not true. But are there any questions about this proof? You'll notice that this one, I didn't give you like a number for this. However, it will be some number. It's highly dependent on what C1 and C2 are and what N1 and N2 are. But the point is that they exist. And so that means I don't necessarily know what they are, but I know they exist. Kind of wild, right? So, are we okay with this proof before I proceed to another property? So I want to talk about another property next. Let's talk about what is called the product rule of big O. At least that's what I'll refer to it as. So some people, by the way, the previous rule, sometimes people call that the sum rule. Product rule of big O. So now this one's going to be a little bit more complicated looking. Just to give you a heads up, it's going to have 4 complexity functions in it. So let there be 4 complexity functions. I'm going to call the first one f1 of n, where I'm going to use a subscript for the 1. I'm going to have f2 of n. Sorry, f1, f2, each with their inputs are going to be n, just to be clear. Then I'm going to have g1 and g2. Now here we go. Here's the property. I'm worried I'm going to start running out of space when I write this out. Would it be okay by any odd chance for anybody if I erase this top part here? Is that okay with everybody? In case anybody's writing down the rest of this proof? Is there anybody that needs to say, Dan, please stop. Don't do it. Okay, I think we're okay. So let me just erase that. Because I need a little bit more space. So we're going to have our 4 complexity functions. So I'm going to have these 4 complexity functions. Then we're going to have the following conditions. If f1 is big O of g1, and f2, I thought the right is, but it doesn't really matter. It's either one's fine. f2 is g2. Sorry, f2 is big O of g2. Then f1 of n, sorry, let's say f1, got to be very particular about this, f1 times f2, I was about to write g, let's write f2. f1 times f2 is big O of g1 times g2. So that's the property here. Now, at first, you might say, Dan, why should I care about this property? Why, like, where would I ever use this? Now, believe it or not, probably in your previous studies, you've been implicitly using this at some point. It's just that you didn't have a name for it. Now, can anybody think about some place where you're measuring operations over, say, you're measuring some operations, but the operations you do first depend on the operations you have to perform before you can proceed to doing another set of operations. So suppose those first set of operations, or how many times you do it, is f1. And whatever you're doing for each one of those sets of operations, you do f2 many operations. And I told you that that first part takes big O of g1, and the second part takes big O of g2. What I'm saying is that you can multiply both g1 and g2 to get your big O result. Now, you might know of a very real circumstance where you've used this before. Or if not, well, you can use a lot of the analyses for searching and sorting. They often will use this, just that we often will count those operations explicitly, but this offers a very general way of looking at it. So think about it. Say, for example, take an algorithm like bubble sort. I know, kind of the whipping boy of sorting algorithms. It is a nested loop, right? So for each one of the elements, you go through a whole bunch, you count up how many times you're going to do that. Well, it's some linear number, right? So you tell me that takes big O of n to go through each of the initial elements, but for each one of those, I do an additional linear amount of work. But that's what a nested loop does, right? So when you've been counting nested loops, for example, very often you'll say, okay, it's this many that are happening on the outermost loop, and then there's this many operations are happening in the innermost loop. And very often you may have been told, maybe even in a previous course, I'm not sure, you may have been told, oh, you can multiply those two counts and you'll end up with whatever that is, that's the big O for it. This is actually just that property. So you'll very often run into this property and how you can use it when you're dealing with nested loops. So when you have like nested for loops, like a for loop where you start from I is equal to 0, you go up to say n minus 1, and then you have another one starts at j, goes up to n minus 1. You know that the innermost loop does a linear amount of operations, assuming all the operations inside of there take some constant number of operations. The outermost loop is linear as well, so you take linear times linear, you end up with something that is quadratic, right? And that's this property. I must stress that sometimes this property is very useful for dealing with nested loops. We're going to see some examples in this course where this property may not necessarily be the one you want to use. Instead, you may actually want to explicitly count all the operations, because sometimes they're spread out in a different way than just the way you might look at it from, say, the standards of, say, a sorting algorithm that you may have seen, like bubble sort. Or, say, I'm just thinking of some other standards nested loop kind of algorithms. But yeah, no, so this is the product rule. The proof for this, the proof is going to be in the notes if you're curious about this. It's in the notes. And now there's another property I want you to know about. This is going to be kind of weird because I only have 6 here and then I have 5 down here. Think of this like a circular list, okay? So here we go. So the next property I want you to be aware of is transitivity. Transitivity. I'm getting my V's and T's backwards. Transitivity. Let me rewrite this. This is one of those days, I swear, man. Let's get this right. We want the transitivity. There we go. Sometimes I have to just rewrite it out for myself, and then suddenly the spelling comes right. Transitivity of big O. So this is a lovely property. This may look like something that should remind you of something. I'm not going to say what. But I'm going to tell you that if F is big O of G, and G is big O of H. So if F is big O of G and G is big O of H, the transitive property tells you that F is big O of H. I like that. I like that. No, wonderful. Yeah, it's kind of like that. So this is the transitive property. Very often we use this whenever you have, say, for example, some intermediate step, and your analysis sometimes can be a little bit tricky. So if you could find out information about this complexity function, and if you know that involves something involving H, you can often immediately infer that F is big O of H. Sometimes there's some analytical thing that's missing in the middle in your analysis. If you can learn more about the harder thing in the middle, you can learn more things about your complexity function. There's several other cases where you'll run into this property, but it's a very natural one for if you want to chain together different complexity functions to say they belong to other ones. So for example, if I have this as, say, n is big O of n squared? Well, n squared, for example, is big O of n cubed, right? So you could conclude in this example that n is big O of n cubed. That's what the transitive property would tell you. So this is a lovely property just to be aware of. And now this one, I'm going to ask you to think about it. So I'm going to ask you to think about the proof for this. I'll give you a tip. It's quite similar to the other one we did. So you might find some bits and pieces of that proof rather helpful for trying to figure out how to prove the sixth property here. So those are all the main ones. I got a couple more I want to throw at you, okay? So I'm going to move on over here. Let's kind of boogie on over here. So I just got to boogie, boogie, boogie. So let's move on over here. This one involves limits. So if it's been a while since you've seen limits, that's okay. You'll find very often I will not invoke this property or require you to use it. I just think it's rather useful for you to be aware of, especially if you're familiar with using limits and perhaps some of your calculus from way back. So I'm going to give you another property. So I'll refer to this as a limit theorem for asymptotic notations. So this is going to kind of put everything together. So believe it or not, there is actually a nice way you could compute limits. And the result of the limit can tell you the relationship f and g have in terms of different asymptotic notation. So I'm going to list out these possibilities, but I must stress that since it is a limit, you have to be aware that there's some limitations when you're computing a limit. For example, you'll see the form I'm going to write up on the board here. So let me just write this first. So if the limit as n approaches infinity, I'm going to be rather kind of loosey-goosey with this. So if the limit as n approaches infinity of the quotient f over g is equal to c, then, so I'm going to have this quotient here. So if I could compute this limit, and if it exists, and there's some value c. So I'm going to think of c as the result of the limit. Now, one bit of warning I can give you is if you try pulling up and picking up this little tool here, sometimes when you compute this limit, you'll get an indeterminate form. So in those cases, you might need to pull out some more calculus and play around with these things. So for example, you may know about L'Hopital's rule. That's where you take the derivative of the top and the bottom, and if you were to evaluate the limit again, you would end up with the exact same outcome. Like that, the desired outcome. And if you keep getting indeterminate forms, you could keep applying this over and over again. But I'm not going to be talking about that here because I want to make sure you understand the definitions fundamentally. I just see this more as a very helpful tool that if you find yourself wanting to quickly calculate offhand, because you know how limits work, how to determine big O, big omega, big thetas, just off to the side if you remember how to compute limits. Then, so if c is equal to 0, then you could say f is little o of g. Now I must stress that when it's little o of g, you guarantee it's also big O of g. So I must stress that this is also that f is big O of g. So if you find that c is not equal to infinity, then you could say that f is big O of g. Then you're going to need, so the intuition here is that if you look at the ratio of these two, as n gets big, as n approaches infinity, you want to see that a certain behavior happens with f and g. So if you know that the g is going to grow so much faster than f does, then most certainly it would be the case that this ratio should approach 0, right? Because this part is going to get grow way faster than the part up on the top here, the numerator. So that's the intuition behind it. Likewise, you know if you end up with something that isn't an infinite quantity, then you know right away you're going to end up with big O. If you get something that's sandwiched in between, so for example, it's some value that's between 0 and infinity, then you could say f is big theta of g. So this is the kind of sweet spot. And then you're naturally going to see that the last two are going to involve big theta. Sorry, not big theta, big omega. Big omega. So if c is not equal to 0, then I could tell you that f is big omega of g. However, if this limit is actually going to be equal to infinity, then you could say that f is little omega of g. And by definition, of course, this simply means as well that that f is big omega of g. Because remember, little o and little omega are just like stricter versions of o and omega. But yeah, this is the limit theorem for asymptotic notations. If you've ever find yourself just fiddling around and you want to just quickly check these things, this theorem is rather handy for doing that. It requires you to be a bit cozy with limits. So sometimes when you're doing this with a little bit more sophisticated functions that aren't just simply polynomials, sometimes you'll end up where this limit is going to be a little bit trickier to compute. Okay? So that's the limit theorem. Now, as I mentioned, when we did this whole process of proving these properties, I often wanted to show it for arbitrary complexity functions, right? Well, sometimes you might think you have some idea of how you could prove some asymptotic property for arbitrary complexity functions. That claim may be true, it might be false. So if it's true, you could naturally write out a proof like we did before, and it should work regardless of what the complexity functions are. However, if there's a problem with the claim, if somebody says, hey, look, Dan, there's a problem with what you just told me, what would be the thing you would try to do to them to convince them? So what would you try to present, not do to them, but present to them to convince them that what they're saying isn't true about that asymptotic claim? A counterexample, perfect. So if somebody gives you a claim and they say, hey, look, I have this wonderful thing, just like what we talked about before, you give them a counterexample. So in the notes, I've included a couple of examples of how to kind of an easy way to present this to somebody. So I'm just going to encourage you to just take a look at the notes. It's going to be sitting right there. It'll give you a couple of examples of how you could kind of proceed with presenting a counterexample in these cases. Wonderful, wonderful. Now I want to give you a couple more properties involving big theta, because big theta has some very neat properties. So many that I may not even talk about all of the possible ones I could talk about with big theta properties. But there's two additional properties I want to point out to you. So these are in addition to the others. So here's a couple that I want you just to be aware of, is that big theta is symmetric. So if somebody tells you, okay, f is big theta of g, this will be the case if and only if g is big theta of f. You might ask, Dan, how would I convince myself of this fact? Now, do you remember the other day I kind of gave you that little bit of a shortcut to think about big omega, right? Where you could just swap the two complexity functions. And I told you, oh yeah, you could divide both sides by the constant and you end up with another constant, right? Well, you do essentially the exact same idea if you ever wanted to prove this. So you start off with your big O claim, your big omega claims, but notice that the way I reorganized them, you could really just say, okay, F is big O of G if and only if G is big omega of F, right? I could swap the two around. So if you find yourself curious about how to try this out, you could just pull out those definitions and use that connection between O and omega to swap them around. I do have actually an interesting question for anybody that's thinking a little bit more about this, I don't know, with the mayonnaise. Thinking about making a mayonnaise, like some sort of epic sandwich. So I told you that big theta, for example, it has the property that if F is the property, so I can tell you that F is big theta of F. Also, I told you that it's transitive, right? I also told you it's symmetric. We have a very special name for those types of relations. Does anybody know what that's called? I'm just kind of curious. I always like to ask these kind of things to see if anybody has any ideas of what that might mean. That's a very special name. I'll tell you, it's an equivalence relation. So what you could do is you can organize all your asymptotic notations into clear categories where they're going to maintain those three properties. There's some other neat things about those, but equivalence classes, they're pretty nifty. You may learn about those a little bit in CS 310. And now another one I want to point out to you, and I mentioned this one already actually earlier. The base of a logarithm is irrelevant. So if b is greater than 1 and a is greater than 1, then log base a of n, log base a is big theta of log base b. So if somebody's working in, say, base 3 versus base 2, you can always switch between the bases. There's a formula for that, the change of base formula. And all it does is it introduces a constant factor to your calculations. And that constant factor is what creeps into your selection of C. Okay? So that's all I have to say about asymptotic notations and their properties. Are there any other questions about asymptotic notation before we proceed? I'm going to talk a little bit about our next topic before we end for today. Because our next topic is pretty interesting. At least I think it is. It's a different kind of question that we haven't probably explored yet in your studies quite yet. So I want to talk about lower bounds. So let's talk about lower bounds. So the next couple lectures we'll talk about this idea. So up until this point, just to give us a kind of a background here, up until this point, we considered statements like there is a big theta of a something time algorithm for blank, where blank is some problem. We've considered things that are like this before, right? If it isn't big theta, it's usually big O, right? So we've always considered statements a lot like this. So that there's some algorithm that solves some problem. Now, often in your studies, you may or may not have had, say somebody tell you, oh yeah, this algorithm is the best possible algorithm under some set of assumptions. You may have been told this at some point, maybe even about sorting, for example, which we will talk about as well here, if that is not the case. So, a natural question is, what do I mean by this? So I want to do a couple of examples of what I mean. So just so that we can talk about what's here in this blank. So for example, when we considered the search problem earlier, you know how we talked about different algorithms we can use to solve different problems, right? If I give you an arbitrary array with no prior information, there's no information I know about the array. You may have been told that a certain algorithm is maybe the fastest you're going to do. Do you know what algorithm that might be? And I'm telling you up front, it's not binary search because I know information about the array in that case. I'll give you a hint. It's the other one we talked about. Think of the search problem. We're not talking about sorting quite yet. Yeah, linear search. Believe it or not, it is linear search. So you may have been told, maybe in the past, if not, we will talk about and prove this in class. That you may have heard that, oh yeah, there is, for example, a big theta n time algorithm for the search problem. For example, linear search, if the set is an array, right? Okay, how about computing the max or the min? So for example, if I give you an array, and I want to determine what the maximum element is or the minimum element is in the array. Could anybody tell me a very natural way of solving this problem? So if I give you an array, and I know no information about the array, other than it's just some array with some numbers in it. Yeah, you do the same idea that we did before. Like when you do a linear search, right? You scan from left to right, you examine all the elements. By the very similar idea, you just do a sequential search, right? So you just scan from left to right, and you hang on to the best results you have so far, right? So sequential search, you could do this in big theta and time. Now, I want to kind of lay one interesting thing on you, and we'll talk more about this next time. But sorting, you've talked a lot about sorting up to this point. Like, I mean, like, you've probably had this problem beaten into your skull figuratively several times over. You've probably seen lots of different sorting algorithms at this point, right? So you may have heard of some, for example, you may have heard of merge sort, for example. You could do, this of course will accomplish n log n time. There's some other ones as well. What if I told you that if I gave you arbitrary elements, that all I could do is tell you that one comes before the other, so-called comparable elements, this n log n time is actually going to be the best we're going to do. And we're going to establish this in the coming lectures, okay? So when we come back, we'll talk more about sorting, just to make sure we're all familiar with the kinds of running times these sorting algorithms have, and different schemes they have. So for example, quicksort, for example, has several different so-called pivoting strategies that change up what the time complexity will be. You may have talked a little bit about that in 210. I'm just going to tell you some interesting things about how you pick the pivot next time. So when we come back, we'll play around with some more about talking about lower bounds. But first, before we have to talk about these so-called upper bounds, the best known algorithms that we currently have for some of these problems. So, that being said, I want to say thank you very much and have yourself a beautiful day. I'll see you later.